Hello, how are you? My name is Jesus Ramirez from Singularity Engineering. I would like to ask you the following question. Have you ever had some problems when prescribing internal boundary conditions? If the answer to that question is yes, this video is for you. In the following minutes, I'm going to explain you how to prescribe an internal boundary condition. For that, I'm going to use the fan boundary condition. Remember, this is Singularity Engineering. Let's start it. To explain how to prescribe the internal boundary condition, I am going to use a very simple model. Here we have two solids. This is the solid and this is solid 1, which has an interface. Then from this simple model, I am going to explain how to set up the internal boundary condition. The first thing we have to do is to prescribe a shared topology among the interface of these solids. Then for do this, we have to move both solids into a new component. Then I will do it. And hence, once we have the solids inside a new component, we select here and we enable the shared topology options. Then, in the interface of both solids, a shared topology will be prescribed when the mesh process is performed. Now, for this example, I am going to use a very simple mesh. Then I have some inflation and multi-sum method for both solids. This is the mesh that I'm going to use to develop the simulation. Uh, An additional step that I have to do is to define some name selection. Then I'm going to name this like outlet. This one I am going to name it as inlet. And I am going to define another one. Then I'm going to quit this one. I'm going to hide it. And here I'm going to call this fan. Okay, and that's it. That's the configuration I'm going to do for the mesh, and I am going to explain the setup of the model right now. Now, in the setup model of Ansys Fluent, we are going to see how the internal boundary condition is defined. Let's see then the parts of the setup that is of interest for us. Then, as you can see, the fan surface is already set up as a fan boundary condition because of the name that I put in the meshing model. Also, this boundary is an internal one because of the shared topology option that was enabled on the space claim. Then this is with this process it's very easy to define internal boundary condition. Here I can change the type, for example, if I want an interior, a perch jump, a radiator, or a wall. Here we are going to use the fan boundary condition. To define the fan boundary condition, you have to select which is the direction of the momentum that is applied by the fan boundary condition. Then here is by default the value, but if you see when you're processing your results that the moment applied by the boundary condition is in the other direction, then you have to select the reverse fan direction. Also, here you will determine the pressure jump of the fan. You can select uh, whichever of these options. Also, you can prescribe a profile for the pressure jump. You can limit the velocity range of the fan, then you will have a minimum and a maximum velocity, which will be will be related with the pressure jump. If you don't want to use this, if you only want to use a only value of velocity, then you can check here and calculate the pressure jump from average condition. Also, if you want to set up zero velocity effects on the flow, then you can switch this one and select which is the fan axis, where is the region, and here are the polynomial coefficients of the tangential and radial velocity profiles. For these coefficients, one option is to know the uh, angle of the blades and calculate or estimate the coefficients for the profile. Just for demonstration, I am going to use the simple mode of this boundary condition. Then I am going to specify only the pressure jump, a constant value of 10,000 Pascal. And right now I'm going to run the simulation to show you the results I got. Once the simulation have finished, I got some results. One important thing is that the outlet boundary condition must be an outflow because pressure outlet is not allowed by the fan boundary condition. Then once the simulation ran, I got these results. Here is the static pressure contour over a middle plane, and here is the velocity, magnitude velocity contour over the same plane. Then you can see here how is the fan boundary condition acting. This is more clear here in the other contour. Here is how the pressure arises after the flow passed through the fan boundary condition. Well, it was a pleasure to me to be with you in this video. If you have any question, please follow us on our YouTube channel or contact us by our webpage or by our phone. Remember, I am Jesus Ramirez from Singularity Engineering. Thank you very much. Bye bye.